Morning. Okay, welcome to Robotics 2. In today's class, our plan is to finish chapter 2 and then I will discuss the solution of project 1. Now, in the last class, we talked about the aircraft roll, pitch, and yaw angles, and finally, we reach the body frame. So, if you recollect, in the last class, we talked about uh, translation from inertial frame. Then we talked about uh, going to vehicle frame. So we did inertial frame. Then we went to vehicle frame. Then we went to vehicle 1 frame. Then we went to vehicle 2 frame. And finally, we reach the body frame. Now, inertial frame to vehicle frame was pure translation, no rotation. Vehicle frame to vehicle 1 frame was rotation in yaw. Then we had rotation in pitch. And then we had rotation in roll. Now, what this means, all said and done, if you look at, if this is our aircraft, then right now body frame is aligned with north, east, and down. So this is the north, this is the east, and this is the down. So we are in the body frame. So this is the body frame. So the roll, pitch, yaw, we took care of that. And now our north vector, or this is also considered as X. This is considered as Y, and this is considered as Z. X is pointing towards the nose, Y is along the wing, and D is going down. Again, please note that this is a right angle triangle, right hand coordinate system, which means your X aligned with thumb gives you Y aligned with first finger and Z aligned with middle finger. So please observe that this is the right hand coordinate system. Now, before we proceed, here is a very fundamental question. And this fundamental question is, why do airplanes fly? So why do airplanes fly? Why do airplanes fly? And I'm gonna quickly give you a basic explanation. What happens is, there is the wing shape is some sort of an airfoil shape. So basically, airfoil is a shape as shown in this figure. And when you have velocity of air, when you have air passing around the airfoil, what happens is the flow splits. The flow splits, and basically the velocity of the air above the airfoil is different than the velocity of air below the airfoil. So for an example, velocity here, I'm going to call this V above, and there is this V below. So velocity above the airplane is different than the velocity below the airplane airfoil because of the shape of the airfoil. So what happens is, velocity below is greater. The velocity below uh, sorry, velocity, yeah, velocity below is uh, is less. Sorry, velocity below is less than velocity above. So what that means is the kinetic energy of the air under the wing is less. That gives rise to the pressure energy, and that means you have positive pressure acting at the bottom of the air. So you have delta P that is acting at the bottom of the airfoil. Clearly, similarly, the velocity above is actually less than velocity below. So what it means is the pressure here is less. So less pressure. So this is less pressure. So that means all in all, because of the incoming velocity, you get something called as the lift. So you have lift. And I want to tell you that this is very easy to observe. That if you place your palm in the airstream, you will realize that you will experience an upward force. And here is something very interesting. This airfoil makes certain angle with respect to incoming stream of air. This airfoil makes certain angle with respect to incoming stream of the air. And what happens is, so think about it like this. If this airfoil is of this shape, if this airfoil is of this shape and making an angle alpha, so this airfoil is making an angle alpha, what's going to happen is airfoil is going to experience a lift. And in addition to lift, there will be a drag. So basically, you will have a lift and then you are going to have a drag. Now, what happens is if you were to increase this angle, and it is called as angle of attack, to a very large value, if you increase the angle of attack to very large value, what happens is there is no lift. All the incoming air, what's going to do is it's going to drag this air back. So there will be just drag and no lift. And this condition is called as stall, which means there is an angle. At that angle, the lift produced by the airfoil is zero. So if you were to look at the plot of lift versus angle of attack alpha, this is angle of attack. What happens is as angle of attack increases, the lift increases, but there is a stall angle. This is called as the stall angle. And after that, there is no lift. There is just drag. And this can be visualized if you place your palm flat in the airstream, start rotating your palm, right hand palm, in the clockwise direction, and you realize when your palm is perpendicular to the airstream, it's going to give you pure drag. And so the aircraft flies because of two things. First is VA, which is something called as the airspeed, and second, angle of attack, alpha. Now, this is precisely the reason why the airplanes need to take off at a high speed, because unless airspeed reaches that particular value, there is no lift sufficient to lift the aircraft. That's why if you look at the airplanes, they have a runway. Airplanes, they have a runway, and towards the end of the runway, what happens is the angle of attack is increased and then the aircraft takes off. Unlike helicopter, aircrafts, cannot take vertically up unless it's a VTOL. So uh, some aircrafts, they can take off vertically like Harriers and Bell 609 tilt rotors, but conventional aircrafts, they need a runway and they need certain speed so that this B airspeed limit is reached, and then there is sufficient lift that is generated so that the aircraft can take off. Now, what this means is airspeed, which is the relative speed of the aircraft with respect to surrounding air. So I need to define this. VA is airspeed is relative speed of aircraft with respect to surrounding, is a very important parameters. And in next few slides, we are going to talk about why is this VA important? Because please try to understand all the aerodynamic forces like lift and drag are generated because of airspeed. And let me show you, if you look at the airspeed is never going to be in the direction of this N. So VA will never be in this direction. It will be at certain angle, or it could be certain angle below. So airspeed, the direction of air relative to aircraft, is going to be in some 3 dimension, and that depends upon the wind speed as well. And that's what we are going to study. Now, just to set the problem up, we are in the body frame. Now, the next frame is something called as the stability frame. So what I want you to observe here, and this figure does not give a very clear picture, but what I want you to understand is, I will try to redraw this figure. So you have this aircraft, you have this aircraft, and what I want you to notice is this, these are the wings of the aircraft. These are the wings of the aircraft. So first and foremost, let's specify the body frame. Let's specify the body frame. In body frame, this is your north, this is your east, and this is your down. So this is in body frame. So this is body, body, and body. So you have north, east, and down. Now, right now, everything is perfectly aligned. Please observe that the airspeed VA, I'm gonna show you the direction of the airspeed, is something in this direction. So I'm gonna just gonna show you. It is like, this is VA. This is the velocity of aircraft with respect to surrounding air. Velocity of the aircraft with respect to surrounding air. Now, what I want you to observe is this airfoil, and I'm going to show you the shape of the airfoil here. So this airfoil, this is the airfoil, needs to be oriented in this direction. So this airfoil needs to be oriented. So if you see from here, if you are here, you will observe that airfoil is something like this. And this angle is called as alpha, which is also called as angle of attack. But for a minute, I want you to look at the direction in which this angle is oriented. And if you look at the orientation in which this angle is oriented, you will realize that this orientation results into the frame orientation that is shown over here. So if you the frame orientation, this orientation leads to the frame orientation somewhere over here. And it's very obvious that alpha, the value of alpha is usually expressed as a positive quantity. But if you look at a frame, if you look at coordinate frame, with respect to coordinate frame, the sign of alpha is negative. So with respect to coordinate frame, and this is important, with respect to coordinate frame, alpha is negative. So that's why when you substitute the value of alpha in the rotation matrices, you will have to substitute as a negative value. So this is the frame that is going to relate body to stability frame. And this frame is defined as the projection of VA. As you can see, the projection of VA in the plane IB and KB. So I want you to define this frame. And you would notice the component of VA in the direction of in the projection of IB KB is nothing but uh, the forms the stability plane I vector. So if you take the projection in the IB KB, that gives you IS, and then you are going to have JS. JS is going to remain in the same direction as JB, and then the cross product is going to give you KB. So what this is angle of alpha, angle of attack, alpha relates body frame to stability frame. And the rotation matrix that governs this transformation is shown over here. And that is actually an important observation. And once again, why do we need stability frame? Stability frame is needed because the aerodynamic forces, they, they, they are resolved in the stability frame. But sometimes the velocity of air A is not in the very clean projected direction. It actually makes an angle which is called as the side slip angle. So for that, let me show you the next frame that is called as the wind frame. Now I want you to notice in the last slide, we assumed VA to be just in the plane, but now this VA is kind of directed inward. So you will notice that this VA makes an angle beta that is called as side slip angle. And this side slip angle takes place because you have wind velocity. Now, this is very important. So sometimes if you have an aircraft that is very large, the wind velocity is comparatively small to the airspeed, so that can be ignored. But in the case of miniature air vehicles or AVs, the wind velocity is anywhere between 30 to 50% of the airspeed, so it cannot be neglected. So if you were to relate and again, this is very important. If you want to relate the stability frame with respect to wind frame, you have a rotational transformation matrix that gives you the a rotational relationship between the stability frame and the wind frame. So please understand what we are doing is, earlier we were in the body frame. Now from the body frame, we went to stability frame, and the angle that is relating body frame to stability frame is angle of attack. Then from stability frame, we are going to wind frame, and the angle that is relating the stability frame to wind frame is the side slip angle, which is beta. So this is angle of attack, and this is side slip. And as you can see that overall transformation, if you want to go from the wind frame to body frame, you have two transformations. First is the stability frame with respect to wind frame, and then the body frame with respect to stability frame. And then when you multiply these two rotations, you get a combined rotation that gives you the relationship or orientation of wind frame with respect to body frame, or body frame with respect to wind frame, depending upon which coordinate system you are looking at. Once again, just for clarification, this is the old frame, this is the new frame. So right now, this expression is the body frame vector with respect to the wind frame. And you can make it's an orthogonal matrix. If you transpose it, you can get the inverse relationship. So what I want you to understand is, because of the air velocity, because of the wind velocity, we need to define two more frames. One is the and the second one is the wind frame. The stability frame comes into the picture because airfoil needs to make a angle with respect to incoming airstream so that the lift can be generated, and the side slip angle comes in the picture because you have the wind, and that actually gives you something called as the wind triangle. So if you look at the interpretation of wind frame, please understand that most naturally, since the aircraft is having non-zero air velocity or airspeed and non-zero wind speed, what we do is we derive the forces in the wind frame, and then those forces can be transferred either into body frame or into inertial frame. So what we are going to do is we are going to derive the expression for forces in the appropriate frame, and then use those relationships to find out the position, orientation, velocity of the aircraft. So once again, a quick recap. What we are doing is we have body frame. From body frame, we have stability frame. And from stability frame, we have wind frame. And please note, forces and moments are naturally defined or derived in wind frame because a UAV typically has significant wind speed and airspeed. And one thing I just want to do, that if you have a tailed aircraft, for an example, if you have a V-tail aircraft, so I don't know if you have seen the aircraft, something like this, wherein you have a V-tail. So V-tailed aircraft. So if you have a tail aircraft, what happens is the slip angle is very small because the tails they try to stabilize the aircraft. Now, what we want to do is we want to give an very important relationship between these three quantities. First quantity is the airspeed. Airspeed is the relative speed of the aircraft with respect to surrounding air. Now, please understand, dynamically, you can treat air, so air around the aircraft to be stationary and aircraft going forward. So you have a VA, which is the airspeed velocity of the aircraft with respect to surrounding air. You have wind speed, and wind speed is dependent on the environment or the currents or the sun's or the temperature change or weather. And ground speed is nothing but the actual speed of the aircraft as if aircraft is traveling on the ground. So if you look at the relationship, this is a vector triangle. If you look at the relationship is VA is equal to VG minus VW, or VG, which is the ground speed, is equal to VA, which is the airspeed, plus VW, which is the wind speed. And this relationship is very important because please try to understand, uh, aircraft, even though we expect aircraft to follow the exact path, aircraft is not going to follow the exact path. And that's why pilot has to do corrections all the time just to keep the aircraft on the proper track. So one thing I want to talk about here is, if we have a ground speed, this ground speed is expressed in the body frame. So let's imagine where the body frame is. Body frame is over here. So body frame is after roll, pitch, and yaw, all the attitude angles are taken care of. So ground speed, when it expressed in the body frame, is given as a component UVW. However, an important note here is the ground speed is defined in terms of inertial frame. So for an example, you have a northeast down inertial frame, and the ground speed is actually defined with respect to inertial frame. But for the purposes of solving and simulation, this ground speed, which is an inertial frame, is expressed body frame. And that is very important. This is very important. So ground speed, so for an example, if you have a GPS and if you try to measure the speed of the aircraft using GPS is going to give you speed in earth centered, earth fixed inertial frame. But based on the roll, pitch, and yaw angles, what you will do is you will convert the earth fixed, earth centered velocity into a body frame velocity. Everybody understood this? This is extremely important observation. So if you have a GPS on the aircraft, GPS is going to give you the inertial velocities, which is in earth centered, earth fixed frame. But based on the attitude angles, roll, pitch, and yaw, you will resolve that inertial velocity into body frame. And that is super important. The next thing is you have the wind speed. Now, wind speed is typically given again in inertial frame. And the reason for that is there are charts and there are relations between the wind speed and attitude, longitude and latitude. So that gives you particular value of wind speed. That wind speed is actually found out in inertial frame, but resolved or expressed in body frame. And why are we doing everything in the body frame? Because we want to derive the equations of motion in a very same and consistent frame. And what happens is, so here is something that is super interesting. So if you look at the the velocity of wind, and if you want to express that in terms of body frame, you have this velocity in the vehicle frame or the inertial frame. And what you do is you use the rotation matrix, to express the velocities in the body frame. So to express in body frame, and this is super important. So please note, this Wn, We, and Wd are the velocity of wind in northeast down inertial frame. Inertial frame is oriented as the vehicle frame. So that's why you have this vehicle frame here, because vehicle frame and inertial frame orientation is same. And this is very important because Wn, We, and Wd, they come from the charts. Those velocities are expressed in the Earth center, Earth fixed coordinate frame, in the same orientation as the vehicle frame. So what we do is we go from vehicle frame, we use this rotation transformation and express the wind velocity in body frame. So what we are trying to do here is this expression Vg is equal to Va plus Vw. This is a vector equation and this is valid. But to solve this vector equation, Vg, Va, and Vw, all of these should be in consistent or in the same frame. Unfortunately, Vg, which is the ground speed that is given by GPS, is given in inertial or the vehicle frame. Vw, which is the wind velocity, is unfortunately given in the wind frame. And Va, which is the air velocity, that could be given in the either in the wind frame or it could be given in the stability frame. So what we need to do is we need to make sure that all these velocities are expressed in the same frame. You cannot add dollars to pesos, dollars to dollars, pesos to pesos. Okay. Does rotation, so remember, rotation B R V, that means you have the velocity or a vector in V frame, and that gives you vector in B frame. So that is what it means is B. So whatever you have here, that is this. Whatever you have here is in this frame. And this is something super important that I want you to be aware of. That's why this expression here is actually B V W, that is B R V, and then you have V, the velocities in the vehicle frame. So this expression is super duper important. Now moving on, what we want to do is we want to find out, finally, we want to find out the air velocity in the body frame. So air velocity is expressed in the body frame, and that relationship is given over here. So this relationship, the point, key takeaway here is ground speed is equal to air speed plus wind speed. But these different speeds or these different velocities are not in the same frame. For this vector equation to be consistent, everything has to be expressed in one frame. And here we choose to express everything in the body frame. So check this out. This is body, this is body, this is body. And check this out. This is G, this is W, and check this out. This is A. So what we are trying to do is, when we try to solve this vector equation, we want to make sure that all these velocities are expressed in body frame, expressed in body frame. And I just want to tell you that when you see this for the very first time, it may sound confusing, but once you spend some time, then you will realize this is just the culmination of what we did so far. But one thing you remember, that vehicle frame and the inertial frame, they have a translational relationship. So there is no angle. So whatever you express in inertial frame, same is going to be in the vehicle frame. That's why you can change inertial frame and vehicle frame interchangeably. Now, once this is done, moving on, you can use that vector relationship. You can use that vector relationship to derive the velocity of air, VA, alpha, which is the angle of attack, and beta, which is called as the side slip angle. And I just want to express this just so that things are clear. Assume, so assume you have a non-zero wind velocity. Assume you have a non-zero wind velocity. So what's going to happen is the airspeed will actually be aligned. Airspeed will actually be aligned in the wind frame. So and I want to give you a very clear understanding of how these frames are related. So bear with me for a second. I'm gonna draw the body frame. So this is the body frame, and this is north, this is east, this is down. So you say this is X in body, Y in body, and Z in body. Now what you have is, you have an angle of attack. So with that angle of attack, what's going to happen is, you are going to have change the orientation, maybe something like this. So this gives you the stability frame. So I'm going to say north stability, down stability, and east stability is aligned with east. Now, if you have a wind frame, what's going to happen? If you have a wind frame, what's going to happen is, there will be a rotation about this guy. So this is north wind frame, east wind frame, and down wind frame. Actually, the wind frame is about the stability frame, so I need to draw this. So this is downwind frame. So what has happened that here there is angle beta and here there is angle alpha. So wind frame orientation angle is completely dependent on the magnitude of the wind. So yes, that can change. Now, so here is how the transformation looks like. But please try to understand, even though it may sound complicated, those are just two rotation matrices that are allowing us to transfer the vectors from body frame to wind frame. Now, if wind velocity is non-zero, the resultant component of VA, the resultant component of VA is actually expressed in the wind frame. So if you look at the wind frame, so and this is super duper important. So this is nothing but VA. The reason you have VA aligned with the aligned with north frame because you have a wind velocity VW, and that is why you have VA. So please understand. Now what I want to do is this VA, and this is super important. Please note this VA is expressed in the wind frame. This VA is expressed. This is expressed in wind frame. That needs to be transferred back to body frame. And only then the airspeed can be expressed in the body frame. So once again, please go back. What are we trying to do? We are trying to express the airspeed in body frame, ground speed in body frame, and wind speed in body frame. Now, when we have a non-zero wind velocity, the airspeed or the aircraft velocity is aligned with the north direction of the wind frame. That's why please note here there is zero, here there is zero, because the wind frame aligns the airspeed to the north in the north direction of the wind speed. So once that is done, this here is nothing but the transformation that is allowing us to transfer the airspeed in wind frame to airspeed in body frame. So this is airspeed in body frame. And once this transformation is done, please note, since there are zeros here, first row, first column gives me, and this is very important, this guy multiplied by this. Second row, first column gives me this guy multiplied by this. And third row, first column gives me, this guy multiplied by this. That's why I have VA over here and this over here. And what that means is I can find out the components UR, VR, WR if, and I can relate those with the wind speed, with the air speed. So airspeed is found out by finding the components of the air velocity in UR, VR, WR, and these UR, VR, WR is nothing but the air velocity in the body frame. And that gives me from a trigonometric relationship that allows me to find angle of attack, So I can find angle of attack, and I can find out side slip. Now, if wind velocity is 0, then the side slip angle is going to be 0. The next important stuff is course and flight path. And course is nothing but the angle that is made with respect to the ground speed vector. So this is called as chi. This is called as chi. And this is called as gamma. So this is called as gamma. So chi is the angle between the inertial frame, inertial north frame to the projection of the ground speed on the flight path. And then there is this flight path angle, which is nothing but it's oriented in the direction of the aircraft, and that angle that is made by the aircraft uh, in the vertical projection, that is nothing but gamma. These two angles, they dictate where the vehicle is headed. So for an example, if you look at, if I want this ground path to be followed, if I want this ground path to be followed, this is the path, but the aircraft is not a car, so it's not going to follow a path like this. Aircraft will have its own roll, pitch, and yaw, and I'm going to express those with respect to the inertial frame. But when I look at the directions and the projection in the plane, which is this plane, this guy, I see that there are two angles. One is chi and the other one is gamma. Now, if I want to show the wind triangle with respect to the ground path, this is how the wind triangle looks like. This is the ground speed, and please note this ground speed is tangent to the ground path. This is the ground speed, and the relationship is Vg is equal to Va plus Vw. Now Vg is tangential to the ground track. You will notice this is the heading or yaw of the aircraft. This is nothing but the side slip angle. This is side slip angle. Then this is the course angle. And what happens is, if you have a non-zero uh, wind velocity, there is something called as crabbing. In other words, the pilot has to continuously adjust the heading. So he needs to continuously change, he needs to crab into the airspeed. So this is called as the crab angle. This is called as the crab angle. And this crab angle takes place because, please note, the aircraft body frame is here. Please note, aircraft body frame is here. But because of the wind speed, what's going to happen is your airspeed has gone over here. And so what you want to do is you want to continuously overcome the wind velocity so that aircraft continues to stay in the body frame. And then the heading is the orientation of the aircraft body with respect to inertial north frame. So this is super important. This aircraft, the triangle. So please note, this is inertial frame. This is inertial. This is the body frame. So this is the inertial eye. This is the body eye. And then heading is nothing but the rotation. You are looking from top view, the orientation change from the inertial to the body. But the aircraft is going to have some sort of orientation side slip because there is some wind velocity. And because of that wind velocity, there is some side slip. And what that does is basically this wind velocity gets added to the airspeed, and that gives you the ground speed. And this is very important because at the end of the day, when we try to derive the differential equations of motion, we are going to use the equation force is equal to mass times acceleration. And in that case, all the velocities, all the accelerations, all the forces, they need to be in consistent or the same coordinate frame. And that's why this aircraft kinematics is super important. So if you look at the wind triangle in the side view, so we just saw the wind triangle in the top view, but if you look at the wind triangle in the side view, you will realize there is angle of attack. This is angle of attack. And this is pitch angle. And there is a difference between the pitch angle and the angle of attack because there is something called as the air mass relative flight path angle. So what this angle means is the wind velocity is not in the plane, but it is in out of plane. So the wind velocity is not completely can be visualized in the flat top view. A component of wind velocity is going in the down direction. A component of wind velocity is going in down direction. That is this component. So wind velocity in down direction. And usually speaking, this wind triangle is a triangle in 3 dimensions. So basically, so when you express this wind triangle on a flat paper, which has 2 dimensions, you will have to draw 2 triangles, one showing the top view of the wind triangle, and this is the side view of the wind triangle. This is the side view of wind triangle. And when the wind speed and side slip are 0, things become super simple. Airspeed becomes ground speed. The velocity equals the velocity to the relative to the air mass. In other words, gamma A becomes 0, and things becomes super simple. The last part in this chapter is what I want to talk about is differentiation of the vector. And I'm not going to go through the derivation, but I'm going to tell you something very simple. Consider that you have a vector x. You have a vector x that is defined as, say, a I. So if I want to find out the velocity x dot, and the reason for this is we did something similar in the robotics one, is first velocity of a dot, or you take the derivative of a plus a I dot. So if you have a vector x which is given as a and I, where I is the unit vector, but if I want to find the derivative of x dot, I will have to take the derivative of first term, and then I will have to take the derivative of second term. Now I dot is nothing but omega cross I. So where omega is angular velocity of frame. So that's what is being shown here. So if you want to take the derivative of the vector, you will have to take the derivative of the magnitude of the vector, and then the unit vector, you will have to cross it, and the order cross product is commutative, so order is very important. This is the angular velocity of the frame crossed with the vector itself. And if you recollect, when we looked at the Lagrangian dynamics in the last part of the robotics 1, we did something like this. And at that time, I showed you the circle of vectors. So I, J, K, and we saw I cross J is K, K cross I is J, J cross K is I. But if you go in the opposite direction, like I cross K is minus J, K cross J is minus I, J cross I is minus K. So we looked at this circle of vectors, and that exactly what this is. If you want to differentiate a vector, you will have to differentiate the magnitude of the vector, and then you have to differentiate the vector itself. Imagine if I is not changing, if I is fixed, in that case, I dot is 0. But when we look at aircraft, usually the unit vector, unless it's an inertial frame, it's not fixed. So we will have to take the derivative of the unit vector itself. So this is the differentiation vector, and that will be useful in the next few classes. But in next class, I will take an example of differentiation of vector to find the velocities. Now we'll move on to the project. In the project aircraft, you are asked to first draw the aircraft, and then the dimensions were given to you, and then do the animation. So what I'm going to do is, now I'm going to go to MATLAB, and I would explain step by step how that problem can be solved. But before we switch to MATLAB, any questions on the material that we have discussed on chapter 2? Any questions on chapter 2? So these notes with my annotation on it, I will upload these notes as in the notes section. So you will have these notes for studying and as reference if they are needed. All right, now we are gonna move on to MATLAB. Okay, can you see my screen? All right, so what I want you to do is, I'm gonna go step by step through the code, and I will show you the Simulink file. So first function is draw aircraft, and this aircraft function needs UU, and these are nothing but the inputs. The function has no output. What are the inputs to the function? The inputs to the function are PN, PE, PD. These are the inertial north, east, down positions. U, V, W. These are the velocities, the body velocity in X direction, body velocity in Y direction, body velocity in Z direction. And this is again in body frame. Phi, theta, psi. This is nothing but the roll angle, pitch angle, and yaw angle. And PQR, these are the roll rate, pitch rate, and yaw rate. And please note, these rates are nothing but the angular velocities of the roll angle, angular velocity of the pitch angle, and angular velocity of the yaw angle. And it is very important, I need to tell you that phi, theta, psi, PQR is, they are with respect to inertial frame. P, N, P, E, P, D are again with respect to inertial fixed frame. However, U, V, and W, these are the body velocities expressed in the body frame. Remember the frame transformation, inertial to vehicle, vehicle to vehicle 1, vehicle 1 to vehicle 2, vehicle 2 to body. So these velocities UVW are in body frame. Everything else is in inertial frame. So then we are describing a persistent variable, aircraft handle, vertices, faces, and face colors. Then first time the function is called, what I'm doing is I'm creating a figure, time t is equal to 0. I clear the figure and then I supply vertices, faces, face color, and those are with respect to defined aircraft body function. This defined aircraft body function consists of V, F colors. So basically V is a set of vertices, F are the forces, faces, and C are the colors. So once I invoke that function, all this data related to size, fuse, all that stuff which comes in this V matrices, F matrices, and color matrices, they are loaded. So F, the matrix for V, matrix for F, and matrix for color, it gets loaded when I call this function. And then what I do is I call the second function, which is called as draw body. Draw body function takes in the input, the vertices matrix, faces matrix, and face color matrix, and PN, PE, PD, phi, theta, psi, all that information. And then it passes to this aircraft handle. So please note this draw body is another function which is over here. So translate, define aircraft. Yeah. So this is the draw body function. And this draw body function has all this input. What it does, it takes V, it actually rotates V, it translates V, and then finally you have the projection matrix multiplying this V, and then what it does, it actually draws the aircraft. And then what I'm trying to do here is I supply a title UAV X northeast down. This is a default view so that the aircraft is properly visible. I set the axis so that the aircraft does not go outside the viewing area, and I add the grid. So this happens when time t is equal to 0 for the first time, and then every time what I do is when new information becomes available, I just draw the body and I supply the aircraft handle. So what it does, this is the pointer to this figure, and then what it does, it just updates the figure rather than redrawing the figure. And this the draw body we discussed, this is something similar to the spacecraft. It is actually drawing the aircraft. Rotate is exact same function, it is rotating. I want you to notice the sequence. You have the roll rotation matrix, pitch rotation matrix, and yaw rotation matrix. They are multiplied from right to left. So yaw to pitch, pitch to roll. And then finally, what we want to do is we have to do this transformation. So that's why you have R times PTS. And then if you want to do the translation, you are going to supply PTS, PN, PE, PD, and that will cause this replication of MAT. The matrix replication will actually add the dimensions to the original points. So it will translate that by X, Y, and Z. Aircraft body function. The defined aircraft body is nothing but is used to actually draw the aircraft. The last V size actually scales the aircraft. Once that is done, I want you to run the Simulink model, which is MavSim Chapter 2 SLX. And I will show you that Simulink model. If if you look at that Simulink model, the Simulink model is going to look like this. It will have U, the PN, PE, PD, UVW, roll angle, pitch angle, yaw angle, and then PQR, and then finally it will have a time variable attached to the clock. This is called as multiplexer. So this actually takes all this information and supplies to this function. This is basically an interpreted S function. That is where this entire code resides. Any questions so far? Now I want you to run this code. I want you to run this code. And once you run this code, you are going to get a pretty looking aircraft. Now, I want you to do something here. First, change roll angle to 45 degrees. Change roll angle to 45 degrees. And change yaw angle to 45 degrees. Change roll angle to 45 degrees and change yaw angle to 45 degrees. And I want you to observe the way the aircraft has rotated. I want you to observe the way aircraft has rotated. Your aircraft has probably rotated something like this. Now I want you to do something. Go back to your code, change the roll angle to be 0, roll angle to be 0, yaw angle to be 0. So now you have an aircraft that is flying towards north, and you have east and down. Now what I want you to do is, this is a very important observation. Please observe this. Change pitch angle to 90 degrees. Change pitch angle to 90 degrees. So once you change the pitch angle to 90 degrees, your aircraft should be going vertically up. So it will be aligned with the down vector. Everyone with me so far? Now what I want to show you is, I want to show you the actual gimbal lock. So what I want you to do is, change roll angle, pitch angle is 90, change roll angle to 45 degrees. Can you see the roll angle is changed to 45 degrees? Change yaw angle to 45 degrees. Change yaw angle to 45 degrees. What happened? The aircraft sort of turned clockwise and turned back counterclockwise about the down axis. In other words, the rotation in roll. Now I'm going to do 90-degree rotation in roll. So 90-degree rotation in roll is about the vertical axis. 90-degree rotation in roll is about vertical axis. And 90-degree yaw is also about the vertical axis. So in other words, roll and yaw, both of these angular variations are in the down axis. So in other words, we lost one axis of rotation. And I want you to try this. At 90-degree pitch, roll and yaw, they coincide. You cannot separate roll from yaw. At 90-degree pitch, roll and yaw, they are one and the same, except one is positive and the other one is negative, because that is how we have defined our angles. This is called as the gimbal lock. So now, if you look at the rubric, I have already posted in the announcement the grading rubric for this project, and this is how the project would look like. And if you have any questions, I would be happy to answer. You are welcome to use the chat window, or you can raise your hand and I will unmute you. So please play with this. No, you wouldn't lose the points. Yes, you really need to submit just the 2 files for the simulation to work, and for the additional information, you can add the description or the text file. You will not lose points if the x-axis are not set to the large value. If you look at the rubric is posted on in the announcement, and rubric for all future, yeah, function is fine. I just grabbed a PNG file and then just replaced that file, tv.png file, and just use that as an icon. But that's okay, you don't need that. So if you click on the draw aircraft, you can actually do the block properties, and then you can actually add the icon. Yep, the due date for project 2 is already posted. So I would look at when the project 2 is due, and the project is due on the due date. Where will you be uploading? Oh, they will be in the canvas. So if you go to canvas, so there is a section called notes, and that is where the annotated PowerPoint slides will be uploaded. I'll show you in just a second. You will have to go to modules, and then there is lecture notes. So let me share my screen. So if you look at lecture notes PPT, and I will just put it next to video lectures. So this is where uh, the PowerPoint slides will be posted. And the links to lecture 1, lecture 2, lecture 3 are already available. Okay, I'm going to stop recording, and I would be happy to answer any more questions you may have.